Check it out now, y'all.
nanoHUB-U, online instruction.
Welcome to Module 2, Week 1. And what we did in Module 1 is I briefly introduced this Schrödinger equation, this differential equation. And as I mentioned, one of the first successes of this equation was that it predicted the correct energy levels of the hydrogen atom. That is, what he showed was, if you solve this equation, which has this form of a E times a function is equal to a differential operator times the same function, acting on the same function. If you solve this equation, it has solutions only for certain specific values of energy, certain discrete values of energy. And those energy levels that you get analytically from that equation for a hydrogen atom, and in a hydrogen atom, of course, that potential energy that an electron sees looks something like this. That is, you have a positive charge. Right around that positive charge, it has the form minus q squared over 4 pi epsilon 0 r. That's the potential around a point charge. So with this potential for U, he showed that you got the correct energy levels that matched the experiment perfectly. Okay. Now, what we'll talk about in this module is, I'll try to explain how you can turn this differential equation into a matrix equation. And that's the version that you don't see as much. You see this, even those of you who are not familiar with the Schrödinger equation have probably seen this appear in different places, the differential equation version. But the matrix version you may not have seen, but that is what we'll be using largely. And in general, it is true that although Schrödinger was able to solve this for the hydrogen atom analytically, there are actually very few real practical examples that can be solved analytically. Most of them require what you would call a numerical solution, namely where you ask a computer to solve it. And the way you usually ask a computer to solve it is, you take this differential equation and turn it into a matrix equation. And a matrix equation, if the matrix is say 100 by 100, it really is equivalent to 100 algebraic equations. Now, as I mentioned in my last module, that with differential equations, there is no systematic way of solving it necessarily. It's sort of like you know the answer and you try it out and see if it works. And if it doesn't work, try something else. With algebraic equations, of course, there's a definite method. You can teach a computer how to do it. And of course, any of us, we could solve a algebraic equation with, let's say, 2 of them with 2 unknowns. That we could do. 3 with some effort. After that, most of us really don't want to do it. But computers, of course, can solve 100 by 100 algebraic equations easily. I mean, in fact, state of the art would be in many, many thousands, really. So once you have converted it into a matrix equation, that's something a computer can actually solve for you. So that's one of the, any method, any actual practical method of solving the Schrödinger equation in a real problem would involve that. In fact, although for the hydrogen atom there is an analytical solution, actually for any other atom you need numerical methods anyway. Like if you, instead of hydrogen, if you are talking about, say, even the helium atom. And the reason is, well, you might say, well, why should that be? After all, helium atom simply means there's 2 positive charges here, right? The nucleus has 2 positive charges. Okay, so the potential is a little bigger. You could put a 2 there. But if someone can solve that equation analytically without the 2, they should be able to solve it with the 2 also. Kind of, but The thing is, as soon as it's not the two positive charges that cause the problem, it's the two electrons in here. You see, there are two electrons now. Just draw that here. A helium atom has two positive charges and two electrons also. And so each electron actually feels a potential due to the other one. And unlike this positive nucleus, which is a point charge, this one is actually distributed over. And so that has to be included in here. You see, that the potential due to the other electron. And that's what finally then requires a numerical solution anyway. See? And this is very real, of course, because how do we know all these energy levels? Well, by looking at how much energy it takes. So for example, one of the ways you measure energy levels of a hydrogen atom, let me just draw it here. So the hydrogen atom, as you know, there is this 1s level, which is the lowest one, which is at minus 13.6 eV. And then there is the next one, which is minus 13.6 divided by 4. As you know, these energy levels of a hydrogen atom, they go as 13.6 divided by n squared. So there's another one here and so on. And the way you measure this energy level experimentally would be hit it with light. As I had mentioned in the context of solids, the way we know the energy levels, the density of states, is this photoemission experiments. Hit it with light, see what energy it takes to knock an electron out. So if you have an electron here, and you hit it with light, what you'd find is it takes 13.6 EV, photons with an energy of 13.6 EV, to actually knock the electron out of a hydrogen atom. Okay. Now I might say, well, what about a helium atom? Well, if you just used U that was twice as big, and you solve the Schrodinger equation, you'd find that instead of 13.6, you'd get something that is about 4 times, 2 squared times as big. You'd find that something was minus 52 EV or so. So you might say, well, in a helium atom, in order to knock an electron out, you'd need photons with an energy of 50 electron volts. I mean, on that order. But the fact is, experimentally, it takes only photons with an energy of about 25 volts, 25 electron volts, not 50. Why is that? Well, because one electron feels a repulsive potential due to the other one. So the other one is sort of helping push it out somewhat. So you really don't need 50 volt photons to knock it out. You only need 25 volt photons. And this is reflected in this additional term that actually has to go in here due to the other electrons. So the first one is due to the nucleus, and then you have to add something due to the other electrons. And that is what makes, what you call first principles calculations of energy levels, much more complicated than the simple hydrogen atom. And all that actually has been done. You see, Schrodinger wrote down his equation in 1925 and, worked out the hydrogen atom. By about 1960 or so, people had more or less worked out the spectra, these energy levels for all the atoms in a periodic table, and compared with experiment and showed that it worked quite well. And that required some amount of, that required computers. I mean, back in the 60s, of course, computers were primitive compared to what they are today, but that was good enough to solve those problems. And then people have looked at solids, molecules and much bigger things like solids. And all of this usually involves turning this differential equation into a matrix equation and then finding the eigenvalues of that matrix. So that is what I want to explain a little further, that this equation in general can be turned into something that looks like this. E times a column vector psi is equal to, actually I'd say more generally I should write E times a matrix S times a column vector is equal to another matrix H times a column vector. So This column vector means, say an array of, let's say 100 numbers. And I'll explain in a minute where the 100 comes from or what that number is. So this is an entire column of 100 numbers. These matrices are 100 by 100 matrices. And that psi again is a column of 100 numbers. So this is what you call a matrix equation. And if you know how to write these matrices, this, then after that, the computer can solve this for you and tell you what the allowed energy levels are. So the overall point is that this is the differential equation. That's the differential equation form of the Schrodinger equation. And you could turn it into a matrix equation, give it to a computer, and then it would solve all the energy levels for you. Now, how do you turn it into a matrix equation? Well, the general approach, the first principles approach is something like this. And let me just write it down, although this is not what we'll be using, but just so you have an idea of how this is done, let me explain. The way you could do it is, you take this psi that you are trying to find and write it as a linear combination of some functions that you know. These are what are often called the basis functions. So you write it as, like, say, psi1 times u1 r plus psi2 times u2 r plus etc. Or compactly I could write it as summation over m psi m u m r. So you could, this is the function we do not know. We're trying to find this function, and we write it as a linear combination of a set of functions we do know and a bunch of numbers here which tell you which are the coefficients, which tell you like, okay, it's 0.7 times this one plus 0.5 times that one plus 0.6 times that one, etc. And these numbers, when you write them in a column, psi1, psi2, etc. So if I had 100 of these basis functions, then there would be 100 of these numbers, which you could write in a column like this, and that is what this is. This is this column vector with all the coefficients. So that's what this one is. And these H and S here, these are matrices, and what one can show, and of course the reason I am not taking the trouble to show it is it's not something we'll use, but I'm just stating it so you kind of have a feeling for how this would be done if you wanted to, is if I want to write down that matrix S, for example, the way you would write it is, the prescription is something like this. The mn element of that matrix is obtained by doing the following integral. dr umr times unr. So these are the basis functions. Actually, to be precise, you should take the complex conjugate of that one. Of course, if you're using real basis functions, you do not need to worry about that. But in general, that should be there. So these are functions you know. So once you know those functions, you can do that integral. And then you get numbers. And these are the numbers that are actually in those matrices. And if you want to write the matrix H, then the elements of that matrix are written by as HMN is equal to integral dr um star. And then you have this H operator. That's that differential operator that appears in the differential version of Schrodinger equation acting on un. See? So, in principle, again, if I know these functions and I have this differential operator, I could do that integral and come out with all the elements of this matrix. See? So this would be what you'd call the first principles way of doing this. And you see, and there are many people who work on that, and there are even software that are commercially available, which does just that. In fact, there is a famous software that chemists use a lot. It's called Gaussian. And the reason it's called Gaussian is that these basis functions they use are Gaussian functions. See? And that allows you to calculate these integrals relatively quickly. Because in a method like this, once you have set up those matrices, after that finding eigenvalues is relatively straightforward. What takes an enormous amount of time is doing all these integrals and finding the elements of that matrix. See? And the Gaussian kind of speeds it up. That's why people develop that, and that's a widely used piece of software actually. Now, where does all that come from? That's what I said. I'm not going into it just because we won't really be using this. That's what we'd be using if we were trying to do a first principles calculation here. Whereas, what we'll be doing is what you might call a semi-empirical method. And the semi-empirical method works something like this. The method that I'll be describing to you. Well, what people do is, they say that, well, instead of finding the elements of this matrix, quote unquote, honestly from first principles, what we'll do is we'll just adjust the parameters a little bit to make sure that it matches well-known results for the material that I'm interested in. So for example, I'm interested in, graphene. And for graphene, people have done experiments, people have done serious first principles calculations. They know what the density of states should look like, what energy levels to expect. So what I'll do is, I'll adjust these matrices first to make sure I get all the right energy levels so that everything matches my favorite experiments. And then, after that, we can use this to do other problems. So in other words, I'm adjusting parameters here to match some experiments, but then going on to explain or predict lots of other experiments with it. See, that's the philosophy of the semi-empirical method. And that's roughly what we'll be doing in this course also. Because again, for my purpose, in this course, of course, what we really want to talk about is the non-equilibrium problem, the current flow problem, which involves not just Schrodinger equation, but involves taking the Schrodinger equation and connecting it to contacts and actually calculating the current flow. And in order to illustrate how you do it, of course, we need some proper description of the channel so that I can tell you how to connect the contacts and all. And as far as that description is concerned, I'll use the simplest one, namely the semi-empirical methods, where generally the way it is done is that this S matrix is assumed to be an identity matrix. Identity means a matrix whose diagonal elements are 1 and all other elements are 0, which basically means you can drop this completely. Because identity matrix, for matrices, this identity matrix is like 1. So in a product, 1 can be dropped. That really goes out. So you can essentially drop that. And the technical name for that, assuming that S is an identity matrix, that says that what you're using is orthogonal basis functions. Now again, if you haven't seen this before, right away that won't make sense, that why orthogonal basis functions should have an identity matrix for S. But I won't go into it. If you're really interested, you can always Google orthogonal basis functions and you'll find out more than you want to know. Anyway, but the point I wanted to make is the models we will be using will assume that this S is an identity matrix, which means it basically drops out of here. And this H will be choosing to, so that it matches certain experiments, what is well known about certain materials, like if you're talking of graphene, if you're talking of silicon, you choose the elements of this matrix so it matches the known properties of those materials. And we'll be using what are called nearest neighbor models. Now, what is a nearest neighbor model? Well, it means that when you take that H and look at the elements H, M, N, the only non-zero elements involve M and N being on nearest neighbors. Now, what I mean by that is, let's say we are talking about a solid whose atoms are arranged, say something like this. And let's say those basis functions are functions that are localized around different atoms. One here, one here, one here, etc. Then the assumption is that this HMN is non-zero only if M belongs to one atom and N is either on top of that atom in the same place or it is the nearest neighbor. But if M happens to be here and N happens to be here, then we assume that HMN is zero. So this is what you'd call the nearest neighbor models. So overall the models we'll be using then, technical name would be its orthogonal nearest neighbor tight binding models. Okay? So in the next module, what I'll try to explain with an example is how one goes about choosing the elements of this matrix so as to match known experimental results.